Hello everyone, myself Dr. Ranjith Kumar Gatla. I am working as an associate professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering. Today, we are going to start another module, the module 5, which is about inverters. And in that, the first topic we are going to discuss, which is single phase inverter and its operation of the single phase off bridge and the full bridge inverter. So, in this module, these are the different topics that we are going to discuss. Of course, only the single phase inverters that we are going to discuss first, then after that we will discuss three phase inverters also. In the single phase inverters, we are going to discuss about mainly the two different types of inverters. One is off bridge and full bridge inverter, and then after we will discuss about the parallel and series inverter, and then the current source inverter, and after that we will also discuss the difference between the voltage source and the current source inverter. Then after we will discuss some modified inverter, which are the McMurray and McMurray-Bedford inverters that we will discuss. Okay. So all these different types of inverters, we will discuss what is the operation of the inverter and how the output waveforms we will get from this operation. These things we will discuss. Then after that, we will also discuss the pulse width modulation technique. And in this pulse width modulation technique, we will discuss the single pulse and multiple pulse width modulation technique, as well as the sinusoidal pulse width modulation technique also we will discuss in this module. Then we will also solve some numerical problems based on these concepts, and finally we will discuss the three phase inverters, the three phase bridge inverters. And in the three phase bridge inverters, there are two different modes of operation. One is 180 degree mode of operation, another one is 120 degree mode of operation. These things also we will discuss. So these are the different topics that we are going to cover in this module. So first we will start with what is inverter, which means what is the basic function of the inverter. Okay, so here it is a device which converts the DC power into an AC power of desired output and frequency is called as a inverter, which means, or in simple words, the inverter can convert DC power to AC power. So which means the fixed DC power to the desired AC power. Desired means variable. Okay, the required AC power. So according to our requirement, the required AC power that we can get. And also not only the variable AC at variable frequency, which means the desired frequency also we will get by using this inverter or the function of the inverter. So the function, the output of the inverter can be fixed or variable. Okay, at a fixed frequency or a variable frequency, which means here the two parameters are there output side. So here if it is this is an inverter, the input that we are giving is DC and the output that we are getting is AC. And here AC, which is the variable voltage as well as the variable frequency. The variable frequency. Okay. So how we will get that, we will discuss while discussing the operation of different inverters. So then for low and medium power, so the transistorized inverters are used for high power outputs. Okay. And SCRs, because there are different power electronic devices are there that we already discussed. Okay, especially the semiconductor devices. Okay, the basic semiconductor devices that we are used to understand the concept of these different inverters is SCRs. Okay, So here these SCRs are used usually in low power applications, okay, and usually the single phase high power inverters, okay, and where the transistorized what is that inverters are used in high power outputs, okay. So this is some basics about the inverter. Then, which means for the inverter we need the DC power input. For the inverter we need the DC power input. So where we are having the output is DC power, at I mean for all those applications we can use this inverter. Like if there is a DC power source but we need, I mean we are having some appliances that will work on AC power, then at that particular place we can use this inverter because that can convert DC to AC. And then fuel cell, the output of the fuel cell is DC, so there we can use inverter to convert the DC to AC. And the photovoltaic array, the PV system, okay, the output of the PV array is also again DC, so again by using inverter we can use, which means these all are the applications of the inverter where we use the inverters, okay. And rotating alternator through rectifiers, okay, so output of this also DC, which means from this we will get the DC output. And hydrodynamic generator, magneto-hydrodynamic generator, the output of this also DC, so here also we can use the inverter to convert into the DC. So there are so many applications are there for the inverters where we use these inverters, okay. Actually, as we know, the pure AC waveform is the sinusoidal, or generally the AC waveform is a sinusoidal, okay, which means the output of the inverter is AC, so it should be sinusoidal, okay. But practically the waveforms are not sinusoidal because it contains some harmonics. So because of the harmonics it may not sinusoidal, maybe sometimes it may be, you may get the square waveform. This is also a sine wave, but because of some harmonics present in this waveform we are not getting the sine wave, the pure sine wave. Instead of this we are getting like this, the square wave, okay. And then how we can minimize these harmonics? And these harmonics can be minimized by using high speed switching methods for the semiconductor devices used, okay. So there are different switching techniques are there, because here anyway in inverters also is a made up of with power semiconductor devices, and the operation of the inverter, I mean how we can operate by just operating the power semiconductor devices. So, and when coming to the operation of the power semiconductor devices is just the switching, which means on and off, okay. So to perform the switching action there are different switching techniques are there, okay. And to minimize these harmonics, okay, so we can operate these switches at high speed switching methods or switching techniques, so that we can minimize the harmonics present in the output AC waveform. And here as they mention, especially for the low and medium power applications, the square wave or the quasi square wave voltages are obtained as inverter outputs, and high power application low distorted sinusoidal waveform can be obtained. So which means again the shape of course not the shape, actually the harmonic content present in the output waveform will also depends on, I mean where in which application we are using this inverter, okay. That will also affect on the harmonic content present in the output voltage waveform. And then what are the different types of inverters then? And here the types of inverters can be classified based on the different parameters, okay. So here first thing is the based on the commutation. We know already what is mean by commutation. The commutation is nothing but the process to turn off the thyristor. The process to turn off the thyristor is called as a commutation. Of course we already discussed different types of commutations, okay. So based on the what type of commutation technique used in the inverter, so we can classify the inverter into the 4 different types. One is the line commutated inverter, and the second one is the load commutated inverter, third self commutated inverter, and fourth one is the forced commutated inverter. Which means in a particular inverter, we use the line commutation to turn off the thyristor. So that kind of inverters are called line commutated inverters. And load commutated inverters, here in the load commutated inverter, the load itself or the nature of the load itself will use to commutate the thyristor, which means we'll use to switch off the thyristor. So that kind of inverters are called as a load commutated inverters. Then self commutated inverters, which means we no need to give any commutation. Okay, which means we no need to use any extra circuit to turn off the thyristor. Okay, so the configuration of the circuit itself will use to turn off the thyristor. So that is the self commutation inverter. And then forced commutation inverter. So which means we need to use some forced commutation techniques as we discussed, like what is that, class A, class B, class C, class D commutation techniques. So any one of the technique we need to use to turn off the thyristors in this particular in a particular inverter, then those kind of inverters are called as a forced commutation inverters. So this classification is based on the commutation, the type of commutation that we are using in a particular inverter. Then the second classification is based on the method of connections. The method of connections. Okay. So in this one is the series inverter, another one is the parallel inverter. Okay. So we will discuss, based on what parameters we can classify series and parallel inverter later on, while we are discussing about series and parallel inverter. That time we will see. But this time you just try to understand the classifications. Then the bridge inverter. Okay. Again, in the bridge inverter, of course, single phase and three phase inverters are there. Based on the supply that we are giving, whether single phase supply or the three phase supply, single phase and three phase. And again, in the single phase, off bridge inverter and the full bridge inverter. Again, in the single phase, we can classify two different types. One is off bridge and the full bridge. These two are now we are going to discuss in today's class. In this class, what is off bridge inverter and what is full bridge inverter, and what is the operation, and what are the difference between off bridge and full bridge inverter, that we are going to discuss in today's class, right? And then, of course, based on number of phases of load. Okay, based on number of phases of load, because as we know, the input is DC, so DC don't have any phases like single phase to three phase. Okay, but output is AC. Okay, so which means the output based on the load, whether you are using the single phase load or the three phase load, based on that we can also classify which is single phase and the three phase inverter. And another broad classification is based on the input source, whether you are using the voltage or the current source. Okay, so if we use the voltage source, then which is called as a voltage source inverter or the voltage fed inverter, but the common word is VSI, voltage source inverter. And if we use the current source, then we usually call it as a current source inverter, because unlike inverters in before we have discussed different types of converters. In all the converters we have used only the voltage source. Okay, we didn't use any current sources, either DC to AC or AC to DC. But only in the inverters there is an extra facility that we can also use current source instead of the voltage source as an input. Okay, so that kind of inverter is called as a current source inverter. So these are the different types of inverters. So we will discuss one by one all these inverters. Okay, so actually in all these inverters, the basic inverters are only two different types. One is voltage source, another one is current source. These are the basic inverters. Again, in the voltage source, you will be having single phase and three phase. Okay, and we will be having the series and parallel. Okay, and we will be having line commutated, load commutated, or self commutated and force commutated. Okay, so which means basically there are only two mainly different types of inverters. One is voltage source and current source. Again, in these voltage source, based on the type of commutation we use, we usually call as line or load or self or forced commutation. Okay, any one of the commutation technique we must use, because here we are using semi-controlled switches, which are thyristors. Okay, so by giving the gate signal we can turn on, but we cannot turn off by just removing the gate signal. Okay, so we have to turn off forcefully. So that's why here, based on the commutation also, we can classify the inverters. Okay, right. Then the first topic is single phase full bridge inverter. So here, this is the circuit diagram of the single phase full bridge inverter, and as you can see here, there are 4 thyristors and 4 diodes are there, and each thyristor each thyristor is connected an anti-parallel diode. Okay, each thyristor is connected an anti-parallel diode, and in between the 2 legs of the thyristor we have connected the load, and we are using one single source. Let us consider it is Vs by 2. This is about the construction of the single phase full bridge inverter. The single phase full bridge inverter. See, you can see, I mean, the circuit configuration of the full bridge inverter and the rectifier. Okay, we can just compare. Okay, so the full bridge rectifier also having the 4 thyristors. Okay, and here the full bridge inverter also having the 4 thyristors. But in addition to that, here we are also having the 4 diodes which are connected anti-parallel to each thyristor. And here another difference is the direction or the orientation of these thyristors are opposite with the orientation of the thyristors connected in the rectifier, because in the rectifier the thyristors are connected like this, right? Okay, but in the inverter it is opposite direction. And another difference is here, the load that we are connecting is in between the 2 legs of the inverter, because this is, let us consider this is leg 1 and this is the second leg. So in between these 2 legs we have connected the load, but in rectifier it is not like that. Okay, so if you just compare the differences and similarities, so it is very easy to remember the circuit diagram. Okay, fine. Then you will go for the operation of this inverter. And here, of course, these thyristors, mainly we use these thyristors only. Okay, so let us consider for our simple understanding. Here I am going to consider only R load. Okay, so initially, and I will draw the waveforms also. Okay, so here this is T, and these are the gate signal. First I will draw for the gate signals, and this is, let me consider for V0. Okay, and this is for I0. Okay, right. So here first the thyristor T1 and T2 are triggered. The thyristor T1 and T2 are triggered. Okay, then which means the thyristor T1 and T2 will turn on. Okay, so here IG1 comma G2, and here it is IG3 comma 4, right? Okay, so first of all I am giving the gate signal, which means gate current is nothing but the gate signal, which is nothing but the triggering. Okay, so I am triggered these 2. Okay, so then the load current will flow from here Vs by 2 to this T12 through load to T22 again here. This is the load current, the direction of the load current, which means here plus and minus. Okay, so here the direction of the current is in this way, I0. Let us consider this is our reference direction, and the output voltage is plus and minus. So then you will get, and how much voltage that you will get across the output, whatever the supply voltage that you are giving, the same amount of the voltage will get across the load, which is V0. So you will get this voltage. right? So then let me consider here the total time period is t. So we have triggered this one for a time period of t by 2. Then for the remaining t by 2, we are triggering the thyristor T3 and T4, T3 and T4. When T3 and T4 are triggered, okay, so immediately the T1 and T2 will get turned off. Of course, here for simplification, I am not including, I didn't include any commutation circuits or any gate firing circuits, right? Okay. So when the thyristors here, which means here T1 comma T2 are triggered, okay. So when T3 and T4 are triggered, then the thyristors T1, T2 immediately get into the turn off. Then the load voltage, the load current will flow from here to T3 to T4 to supply. So which means here the direction of the current is in opposite direction, and the voltage terminals also has been changed. Okay, then of course then here you will get the negative voltage. For this duration. So here the magnitude is Vs by 2, and here this negative magnitude is minus Vs by 2. Then this the process will continue. Then after this again the T1 and T2 is triggered. Then again you will get the positive voltage across this. Then again negative voltage and positive voltage, like that. We will get the output voltage waveform. Here you can see this is the output of the inverter is AC, but here we didn't get the sine wave, but instead of that we have get the square wave, because as we discussed, okay, because of the harmonic content present in the output, we will not get the pure sine wave. Right? So this is about the output voltage waveform, and this is the process of the the single phase full bridge inverter. Then you may get a question or doubt, what is the use of these diodes D1, D2, D3, D4? Of course, when we use the R load, there is no function of the diodes, so we can just simply remove from the circuit also. But when we use RL load, then the function of D1, D2, D3, D4 will come into the picture. Because here, if it is an RL load, so while let us consider T1 and T2 are triggered. While T1 and T2 are triggered, okay, so here the inductor will get charged. Here the inductor, because RL load is there, inductor will get charged. Okay, then after that we have to provide the discharging path for the inductor. Okay, so to provide the discharging path for the inductor, okay, so the discharging current, so we will utilize these diodes. Okay. So for that purpose only we are connecting the diodes are anti-parallel with each thyristor. Okay, otherwise with simply R load, we no need to use these diodes, and there is no function of the diodes here. So that's why for our simple understanding purpose I have considered R load. So that's why I didn't utilize these diodes. Okay, so the diode function is when there is an RL load, that time only we will use this diode function to discharge the current. To discharge the inductor, right? So here, see, that's what here IG1 and IG2 are, we are giving the gate signal for IG1 and IG2, which means T1 and T2. Okay, so T1, T2 are triggered, then we will get the total voltage. Okay, if it is Vs by 2, here we will get the Vs by 2. Otherwise, if it is Vs, then we will get the Vs. Okay. So based on the input supply that we are having, so which means here T1 and T2 are triggered, and then when IG3 and IG4 are giving, which means the gate current for the third thyristor and the fourth thyristor, then the T3 and T4 will turn on, then you will get the the negative voltage. Then after that again positive and negative. So here usually we are taking for our simple understanding purposes. So here we are the time period, I mean how long the thyristor T1, T2 will turn on means, let us consider here this is the total time period T. This is the total time period T. Okay. Then T by 2, for the duration of T by 2, the thyristor T1, T2 will turn on, and for the duration of again another T by 2, the thyristor T3 and T4 will turn on. Okay, so very simple, right? Then we will discuss the single phase outreach inverter. Single phase outreach inverter. So here, as you can see in the single phase outreach inverter, here it was mistake. It is T and T. Okay, so T1 and T2. Let us consider. Okay, then in the single phase outreach inverter, so here as you can see we need two sources. Okay, one is Vs by 2 and another one is also Vs by 2, but these are the symmetrical DC sources that we are using, Vs by 2 and Vs by 2. Okay, and two thyristors. Okay, so here as you can see, of course the waveforms are again same. So initially first the thyristor T1 will turn on. The thyristor T1 will turn on. So when the thyristor T1 is turned on, then in this case the source Vs by 2 is utilizing. Then here the load current will flow through the load in this way. So which means in this direction. Okay, so let us consider here A, B. So in this case B to A is the positive direction, which means our reference direction. Okay, then when the thyristor T2 is triggered, then the another source Vs by 2 will utilize, and in this case the current will flow in this way, in this direction. So which means as you can see the current flowing through, the load current flowing through the load when the thyristor T1 is triggered is from B to A, and when the thyristor T2 is triggered and the current is flowing from A to B through the load. So which means both are in opposite direction. So that's why here also we are getting this is Vs by 2 and another one is also Vs by 2 during the negative. Of course the current waveform also you will get the same waveform, because here also we are considering R load. Okay, and here also the function of the D1 and D2 will get into the picture when we consider the RL load. Otherwise there is no function of this D1 and D2. So this is about the operation of the single phase, full bridge and half bridge inverter. Then what about how to find the average or RMS value of these output voltage waveform? Okay, as you can see here the time period is T by 2 that we are considered. Okay, the time period is T by 2, and from 0 to T we are getting the positive Vs by 2, and during T by 2 to T we are getting the negative. Okay, so that's what here. Of course for average, well, let us consider for V average, which is equal that the standard equation is 1 by T into integral 0 to T, 1 by T into integral 0 to T Vm sin omega T into d omega T. Okay, but here instead of sine wave we got the square wave, so that's why here 1 by T. Of course here also the total time period is T, and here we are having the two functions. Okay, but of course in the two functions the shape of the waveform is same, symmetrical. Okay, so that's why here 0 to T by 2 Vs by 2, the voltage we have considered the maximum magnitude is Vs by 2 into dt plus T by 2 to T again Vs by 2 into dt. This is the average value. And RMS value here as already they have written. Okay, so which is 1 by T into integral T by 2, because for RMS value the standard equation is 1 by T into integral 0 to T Vm square sin square omega T into d omega T whole to the power of 1 by 2. Okay, so here again this is the total time period, so that's why the total time period of this waveform is again t that we have considered. Okay, then here this total waveform, because from 0 to t, okay, so 0 to t by 2 we are getting the positive waveform, and t by 2 to t we are getting the negative waveform. So that's why we are dividing into two functions. One is integral 0 to t by 2 into vs square by 4, okay, which means actually vs by 2 whole square, which is nothing but vs square by 4, plus again t by 2 to t vs square by 4 into dt whole to the power of 1 by 2. So if we simplify this, okay, then you will get the VRMS, which is equal to Vs by 2. Of course, more or less, if you simplify the V average also, you will get the same Vs by 2 for both. What is that? The single phase full bridge converter and the half bridge converter, especially for the voltage VRMS and V average. But in coming to the current waveform, okay, in the current waveform also, if you consider R load, you will get the same like the voltage waveform, okay. So but if you consider RL load, the voltage waveform and the current waveform are totally different, because of the inductor effect, it will charge and discharge. So while turning of the thyristor, okay, so during the turn off of all the thyristors, the inductor will get into the picture, and inductor will supply the current, a small amount of the current to the load, okay. So and in that case, what is that, the load will supply the energy to the source, okay. So in that time, the the diodes will get into the picture, okay. So that is this is all about the inverters, okay. In the next class, we will discuss about the series and parallel inverter. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.